In this video, I'll be taking some examples for the RSA system. In my last video, I've explained what is the RSA system. This is the public key cryptography system, and in this public key cryptographic system, say two people want to communicate. Elias and Bob want to communicate some message securely. So Elias has some public information, and what is the public information with Elias? That we write it as N and E. N is the product of two large prime. So N is the product of two large prime. So private information, so this P and Q, which is the primes, and they are 100 digits long prime, they are not informed. So this P and Q, they are kept secret. And we also have one more integer D, where D, this into E is congruent to 1 mod phi of N. And also in this setup, the GCD of E and phi n, this is equal to 1. And we also notice that phi n is always even whenever n is strictly greater than 2. So E that is selected by Elias is always an odd integer. Now with this information, suppose Bob want to communicate a message M. This is the message. So Bob do not send this message in the current format, rather it is converted into some cipher text, and that cipher text I am using with the symbol C. So C is congruent to M to the power E. So Bob knows the public information. E is already public. So M is the message which is already there with Bob. So Bob can find the cipher text with respect to mod N and send C to Elias. So now Elias knows C, and Elias already have this information PQD. So Elias calculate the original message M, which is congruent to C to the power D mod N, and the original text or the plain text is read by Elias. I've explained in my previous videos these setup, their algorithm, and I've also explained a theorem which correspond to the justification why these two congruences are valid, and they are valid because M to the power ED is congruent to M mod N. So we have proved that this is true with this sort of setup that I've explained, and hence these congruences follow up. So the RSA system works. So now in this particular video, I want to take up some examples for the RSA system. Now in this question, the message M is encrypted using the RSA with modulus PQ, or we can say if N is given, we know this is a product of two large prime P and Q. With the encryption exponent E yielding some cipher text, find M. So we need to find what is the original message with the information. Now there are two parts for this problem. Let us find the solution for the first part. In the first part, it is given P is equal to 3 and Q that is equal to 23. So let's find N. The modulus N, which is PQ, this is equal to 69. We also know E, that is the encryption exponent 3. So with the public information as I've just said earlier is N and E. Both of these we know. N is 69, E is 3. Let's look what should be the private information. In the private information, we should have P, Q and D. P is the prime, and we know that P is 3, Q is 23, but we do not know what is D. So first thing that we must need to calculate D. To calculate D, we should have calculated ED, that is congruent to 1 mod phi n. Phi n is the Euler-Stotian function. You can see that in my previous video. E is 3 into D, that is congruent to 1 mod phi n, because n is the product of 2 prime. So phi n is P minus 1 into Q minus 1, that is congruent to 1 mod 2 into 22. So we know the value for P and Q, and so we can calculate this. This is congruent to 1 mod 44. So now to find this value for D, either we can try all possible values for D quickly by trial 1, 2, 3, 4, so on, and we'll find D is equal to 15. Because 15 into 3, that is 45, minus 1 is 44. So this work D equal to 15. So we have now information to D. If we do not want to try this by trial, we can see this is like 3 into X plus 44 into Y equal to 1. And here we can apply extended Euclidean algorithm to solve this problem. 44 equal to 14 into 3, that is 42 plus 2. So 2 is the remainder. Now this acts as quotient, this is divisor, plus this is remainder. And then we again repeat this process. 3 equal to 2 into 1 plus 1. So now you can see that now the quotient is 2 and the divisor is 1. 1 is equal to 1 into 1 plus 0. So this is normal Euclidean algorithm. If I follow the reverse process, and here actually when we get it as extended Euclidean algorithm, pick up the last non-zero remainder, that is 1, equal to 3 minus 2 into 1. This is equal to 3 minus the previous last remainder is 1, 2. So replace now this 2, 1 into 44 minus 14 into 3. This is equal to 3 minus 1 into 44 plus 14 into 3. So now we club these to 1. We get 14 plus 1, that is 15 into 3 minus 1 into 44. So we can see what is the coefficient of 3 here, that is 15 now. Or you can say 15 is multiplied by 3. So this is like a linear congruence. We can solve this linear congruence by various different methods. And we have calculated D. Now once we have calculated D, we have been given the C to us. So we want to now calculate the original message. Original message is C to the power D mod N. So here we have C as 9, 9 to the power 15 mod N, and N we have calculated as 69. Now here I want to again use binary exponents calculation, and so I find this is congruent to 6 mod 69. To do this portion, you can again see my previous videos. So this is something like 9 is congruent to 9 mod 69. Then we raise 9 square. This is congruent to 81, and find this is congruent to 12 mod 69. Then I again raise 9 to the power 4. This is congruent to 144. This is congruent to 6 mod 69. Then we have 9 to the power 8. That is congruent to 36 mod 69. Now because I want to reach to 9 to the power 15, this is congruent to 9 to the power 8 into 9 to the power 4, 9 square into 9. And we have already calculated some of these in the reduced form. So again when I multiply, we get that this is back to the congruent to 6 mod 69. So this way we find that the message M is congruent to 6 mod 69. And now somebody want to know what is the corresponding alphabet or what this message was correspondingly. So if we are using the standard conversion of the alphabet, A correspond to 00, B correspond to 01, C correspond to 02, and so on. Z will correspond to 25. In this we can see that M equal to 6 will correspond to the letter, or we can say this will correspond to the plain text as G. So this completes our first part, and on the similar line you can try for the second part. So this I am not doing, this I'll leave for you as an exercise. Now we'll move to the next question. Now in this example, we consider that we are working with RSA Cryptosystem, and we just want to verify that can we find the decryption exponent D for the following A part and B part. So here we can see that for the following A part, in this P is equal to 7, Q is equal to 11, but we notice that E is 6. And here we'll say no, we cannot find the decryption exponent D. The reason being that the GCD of E and phi n must be equal to 1. But here we notice that E is 6 and phi n, as I've just explained, phi n is even whenever n is greater than 2. We can notice that phi n, this is equal to P minus 1 into Q minus 1. P minus 1 will become 6 because P is 7. So this is 6 into 10, that is 60. So this is even. So if I just replace this here 6 comma 60, you can see both of these integers are even. So the GCD is greater than 1, or we can say this is not equal to 1. So we cannot find the decryption exponent. We must take care of the setup that we have earlier set it up for the RSA. In the B part, P is equal to 11, Q is equal to 13, and E that is equal to 7. So here we can definitely say yes, we can find the decryption exponent, and this is found by ED congruent to 1 mod phi n. Again I am going to use extended Euclidean algorithm for this. E we already know 7. This is congruent to 1 mod 120. How I got 120? This is P minus 1 into Q minus 1. So that is 10 into 12, 120. So we find that this D comes out to be 103. Only unique solution will be given here. Because the GCD of 7 and 120 is 1 and that divide 1, this is like a linear congruence, we'll find a unique solution here. So we find D is equal to 103. That is the decryption exponent. In this third example, again we want to encrypt the message M using the RSA system. Here we want to have the encryption, that means ciphertext we want to find because the original message is given, and with the other information P, Q and E. So in this question, let's quickly first find N, that is the product of PQ, which is 91. We also require phi N, that is equal to P minus 1 into Q minus 1. So this becomes 6 into 12, which is 72. And we require ED, this is congruent to 1 mod phi N, because we need to find what is D, decryption exponent. So D is equal to 29. To find this D, that is equal to 29, what I just have done, I simply substitute the value for E, which is 5, into the, this is congruent to 1 mod 72. And as I did earlier, this I can write as 5 into X plus 72 into Y equal to 1. I apply here first Euclidean algorithm. So when I apply here Euclidean algorithm, so I want to first find the GCD of 72 and 5. So 72 is 14 into 5 plus 2. And then I take next divisor 5 and remainder. And I continue this process, which is standard for the Euclidean algorithm. Then from here I follow the reverse process. The last non-zero remainder, that goes here 1, which is 5 minus 2 into 2. This is equal to 5 minus 2 into previous last remainder, that is this 2. Now I'm just replacing this 2 here. That will become 72 minus 14 into 5. So we get 29 into 5 and minus 2 into 72. So we see that 29 is multiplied by 5. So this way, either we solve it as a linear congruence. I've added the link to all this topic in the description box. These are, I have already explained how to apply Euclidean algorithm, extended Euclidean algorithm, or how to solve the linear congruences. Now from here I found the value for D. Once we find the value for D, so now I just need to find what is C. C is congruent to M to the power E. If you know M, then this would be the formula mod N. And if we know somehow the ciphertext, in that case, to read original message, we should know C to the power D mod N. So it depends. If we know ciphertext, we'll be going to use this one. If we know the message, then we are going to use the encryption. So here C is congruent to M is 5, E is 5, mod 91. So C, this is congruent to 31 mod 91. And again, to find this 31, I have used the normal calculation of the linear congruence, like 5 is congruent to 5 mod 91. Then I take the binary exponent 5 square, that is congruent to 25 mod 91. Then I will again take, this is 5 cube, which is congruent to 125. This is congruent to 34 mod 91. Either you can do this one by one, or you can take binary 5 square, 5, 4 and so on. But since I just required 5 to the power 5, so I've just found this consecutive square powers. 34 into 25, this is congruent to 850. 850 is congruent to 31. So basically this is the least remainder when it is divisible by 91. So we find that ciphertext is 31 in this particular question. And that is what we require, encrypt the message. So for this message, the encryption is 31. Now in this example again, there is a similar question. We want to find D, decryption exponent, with the information this. And for this, we just notice that N is 33, which is the product of P and Q. Phi N, this is 2 into 10, that is equal to 20. So E into D is congruent to 1 mod phi N. And so we get 3 into D, this is congruent to 1 mod 20. So now again, using the same extended Euclidean algorithm, we can find D is equal to 7. That becomes the decryption exponent. Now in this example, Romeo said Juliet the hour at which they will meet. He uses RSA with P equal to 3 and Q equal to 17, E equal to 5, and the ciphertext C equal to 3. When will they meet? That means we want to find what is the original plain text or the hour which has been communicated between Romeo and Juliet. For this, and it is said that we are using RSA setup. So N is equal to PQ, which is the product of the two primes. So in this case we have 3 into 17, which is equal to 51. E, that is the encryption exponent, which is 5. Let's first find what is D. So ED is congruent to 1 mod P minus 1 into Q minus 1. So this is congruent to 1 mod 2 into 16, or so from here we can get 5 into D, that is congruent to 1 mod 32. Now using the same standard method, I'll calculate D is equal to 13. Once we know that D is equal to 13, so we know the original message is C to the power D. C is already shared with us, that is 3. So 3 to the power 13, and 3 to the power 13, that is congruent to 12 mod 51. To know that why 3 to the power 13 is congruent to 12, we are going to use the same. 3 is congruent to 3 mod n is 51. Then take 3 square, which is congruent to 9. Then take 3 to the power 4, which is congruent to 9 square. 9 square is congruent to 81. 81 is further congruent to 30 mod 51. So we'll just reduce this. 3 to the power 8, which is congruent to 30 square. 30 square is congruent to 900. 900 is congruent to 33 mod 51. And then just club, because we want to reach to the exponent 3 to the power 13. So this is 3 to the power 8, 3 to the power 4 into 3 to the power 1, which is congruent to 33 into 30 into 3. So I've just substituted back the values that I've just calculated earlier. So with respect to mod 51, and when I take the product, this becomes 2970 divided by 51, and find the remainder. Remainder is 12 mod 51. So this is how I got 12. So you can see that we need to know how the congruences are working. So in case you are making an algorithm, so you need to know how these binary algorithm work, binary calculations, or the binary exponent work calculation is done in the congruences, so that we can apply this in the RSA setup. So here in this question, the answer is, when the Juliet meet, the answer is at 12 hours. So that is the answer for this problem. Now in this sixth example, let Bob want to send Alice the message help. Alice chooses her secret prime P and Q and the encryption exponent E, and she calculates N, which is this large integer. So here you can see that this problem becomes difficult if the primes P and Q which are selected, they are 100 digit long prime, and so we then calculate N. So obviously the calculation of phi n becomes difficult. So these all are quantities that these all integers that are selected, they are random integers. Even this encryption exponent, we said that this has to be an odd integer. So here this is why random numbers comes into the picture of the cryptography. But just for the purpose of understanding, I'm using some of the data that I've calculated from a program. What ciphertext C does Alice receive? And as we know, for the first case, we should know C, this is congruent to M to the power E. We already know what is the message. So message has to be calculated from the help. Message is help. So if it is an English alphabet, we must first need to convert this into the digits. So its numerical digits are, and here I am using the standard terminology, A as 01. You could have also taken A as 00 and then Z as 25. But here I just consider A as 01, B as 02, and I am considering Z as 26. So once I take this standard terminology, help, this is converted into the digits, that is 8051216. So this is the digit which I am using for help, where H stands for 8, E will stand for 05, L will stand for 12, and P stands for 16. So when you just write all these numbers together, this becomes 8, 05, 12, 16. Now this is the message, so that is 801511216 and raised to power E. E is already given to us 2347. With respect to mod n, we see that n is a very large integer here, so I'm just writing this as n. Now solve this exponent. As you can see that this is not easy. It's not easy. Somebody can do it manually. You definitely require a computer program to calculate this thing for you, and when we calculate, we find that this is the large integer like this. So this is the ciphertext which is supposed to should be the answer of the first question. So C is the what alias receive. Now in the second part, we want to verify alias decryption exponent. For the decryption, ED should be congruent to 1 mod phi n, and in the same procedure, we know what is E, we know what is phi n, we can find D. So D is going to come up here as 53380876259. And for the C part, we want to verify original message back. So original message M, this is congruent to C to the power D. C we know in the first case, D we already know from the second part. So we are going to verify that 8051216, that is the original text, and here we get back to the mod N. Now in this example 7, I'm not going to solve this question as a full, rather I'm just going to add certain hints, because for this we require a computer and a program to do the calculation. But let's see what this question is so that I can just add certain hints or the direction by which this question can be solved. We have this RSA system, and for this the encryption key is this. So we know what is E and the N. The ciphertext received is this, where each block is encrypted separately. So let's see, in the RSA system we require certain information which is public, that is N and E. So we already have the public information. N is 31439 and E is 17. Now we are looking for some private information to know the process, that is P, Q and D. So P and Q, these are the two primes from which that is equal to, so that N is equal to PQ. So these are the two prime whose product gives me the N. So this is the first problem about the factorization. Why we require to know how we have a factorization, or why this factorization is a very important problem in number theory and cryptography. There is one method of the factorization which I have explained earlier in my videos, Fermat's factorization method. And from that Fermat's factorization method, we see that you find the under root of 31439, and we find that this is approximately 177. Now you try looking 177 square minus 31439. This is equal to some integer, and if this some integer is a perfect square, then we can do the factorization. Otherwise we start increasing this exponent. We find gradually that this is not an perfect square, this is not a perfect square, and earlier also this is not a perfect square. But at 180 square minus 31, okay, so let's write 31439, this is equal to 31 square. So which means I have now a system 180 square minus 31 square, this is equal to 31439. So this will allow me to write a factorization like 31439, this is 180 plus 31, and then I have 180 minus 31. So this will become 211 into 149, and we find these both are prime. So maybe this we can take it as P and this you can take it as Q. It doesn't matter which is the smaller, P or Q. Now these two are the prime. So this is how first step is to find the factorization if you know the N. But this is not an easy problem. If you have hundreds of digits in each prime, obviously N is then very large. This is why the RSA system is considered very secure. But let's say because still these are finite integers, and we have found the first step that we have factorized this, which means in the private information we have found P, we have Q, and now I need to know the D. So for D, you need to know what is the solution of this congruence mod, because I know now this is P minus 1 into Q minus 1, 210 into 148. So here I'll say 17D, this is congruent to 1 mod 210 into 148, and this when I multiply I'll get 31080. From here I want to solve this D, and for this I'll be using extended Euclidean algorithm, the same procedure. But you see that whenever these integers are getting large, you require the help of the programming. So we find that D comes out to be 7313. Now once the D is calculated, and look at this individual block, say this is the cipher text as it is given. I want to find original message. Corresponding to this, the original message is, let's call this first block as C1, Let's call this one as a C2 and this one as a C3 and so on. So I have first message which is congruent to 3807 raised to power d, that is 31 this mod with respect to n. And similarly I'm going to find M2. So M2 would be the second block of the plain text. So let's write here that I'm going to find the plain text. Similarly I'll find M3, M4 and M5. So these are the calculation as I've done earlier in my example. So this will be 26663 and the exponent will remain same 313 because the d is same mod n. So this way you can explore this onto the computer programming and you can find the corresponding plain text. This is like an example of a block cipher as well. Each block is encrypted separately using the RSA system.